This is a difficult and lengthy related rates problem, but we will do our best to work through it in as logical a manner as we can. So again, let's read the question. Suppose you drink water from a conical cup through a straw. The cup has diameter 8 centimeters, depth 10 centimeters. You drink 7 cubic centimeters of water each second. That cubic centimeters tells you that we're in the realm of volume again. At what rate is the level of liquid in the cup falling when the water is 6 centimeters deep? Okay, so let's define some of the variables that are going to be involved here, and we need to define them pretty carefully. So let's say that V is the volume of, let's say VC is the volume of the cup, and VW is the volume of the water in the cup. Let's also say that RC is the radius of the cup, and RW is the radius of the surface of the water. In the cup. Now, some of these variables we may not actually need, but it's a good idea to list them all before we start. Let's say HC is the height of the cup, and HW is the height of water in the cup. Okay, so this time I think a diagram is going to be very necessary. So we have a right circular cone, and you know these are the types of cones, the types of little paper cups that you get in water fountains. So something like this. And so let's say that's your little paper cup, and within that then we have the water. So let's draw in some water here. Okay, so there's the water within your cup, and hopefully that's clear enough to you. And then just to make some of the dimensions a little bit more clear to you, go up from here at right angles to the surface. Okay, and that is the radius of the cup. Now we were told the diameter of the cup. If you go back and read the question, you were told the cup has diameter 8 centimeters, so its radius will be 4 centimeters. And we also know the height of the cup. By that height of the cup, and we were told, if we go back up, the cup has diameter 8 centimeters and depth and height are the same dimension, 10 centimeters. So the height of the cup is 10 centimeters. Now, what we'll do next is we will mark in these measurements, but we will mark in the quantities, but we won't actually mark in the measurements that relate to the height of the water. We'll just call it HW, and we'll call this RW. And the reason we don't mark those in is because they're changing. As you drink water out of this cup, the height of the water, the depth of the water, and the radius of the surface of the water are changing. So we won't mark in anything that is changing. Okay, so let's go back and read the question again. Let's figure out our known rates and our desired rates. So it tells us that you drink 7 cubic centimeters of water every second. That's the volume of water. Okay, and it's changing by 7 cubic centimeters per second. So that's the first thing. That the volume of the water, so the known rate, is dV VW dt is equal to, now you're drinking 7 cubic centimeters of water every second. In other words, 7 cubic centimeters of water each second is leaving the cup. And VW is the volume of water in the cup, so it's actually been reduced. The amount of water in the cup has been reduced. So we're going to say it's equal to negative 7 cubic centimeters per second. So that's the first thing. Okay, pay attention to that negative sign, because the amount of water in the cup has been reduced. The desired rate, and I'm sorry for having to scroll up and down all the time, but the desired rate, at what rate is the level of liquid in the cup falling when the water is 6 centimeters deep? So in other words, the level of liquid, the height of liquid, the depth of the liquid, and that quantity we've called HW. Okay, so that's what we want to find. We want to find how quickly the height or the depth of water in the cup. So dHW dt, that's what we're looking for. Okay. Well, we know that the water in the cup is in the shape of a cone. And water takes the shape of its container, so in this case it's a cone. And the formula for the volume of a cone, which you would be given this formula, would be V, in this case we'll make it VW, is equal to 1/3 pi R, or RW, again RW squared, HW. Apart from the subscripts, the W subscripts to indicate that we're talking about the water here, that's the formula for the volume of a cone, and you would be given that formula. Now, this formula has 1, V, R, 2, and H, 3 variables. Okay, those are 3 variables. So that means when we differentiate this, we're going to have a dV dt, a dR dt, and a dH dt. We know dV dt, and we want dH dt, but the dR dt is going to present us with a problem because we don't know it, and therefore we can't substitute a value for it. So we have to come up with some method of working out what that may be. And this relies, and you're not told this, there's no indication that this is the case, but this relies on you knowing a little piece of information that you'd have learned when you studied cones. That the volume, not the volume, but the radius of the cone divided by the height of the cone is equal to the radius of the water within the cone, and we'll call it the water surface, divided by the height of the water. Okay, now we can put our own variables on that. The radius of the cone, if you check up here, the cone or the cup, these are all labeled here. So if we use that, the radius of the cone or the radius of the cup we called RC, the height of the cone or the height of the cup we called HC, the radius of the water we called RW, and the height of the water we called HW. Now RW and HW are changing, we can't replace those, but RC and HC we know. RC is the radius of the cone, that's 4. So if there are terms which don't change, that are constant, you can plug those in. For the height of the cone was 10. So we have 4 over 10 equals RW over HW, and we can break down this variable, or this fraction on the left, that's 2/5 is equal to RW over HW. And now this is useful to us because we wanted to get rid of RW. If we go back over here to where we had our original work, we had the volume of water in the cup is equal to 1/3 pi R squared WHW, and we wanted to get rid of the R squared. So this allows us to write our W in terms of H. So if we multiply both sides by HW, we get 2 times HW over 5 is equal to RW. Okay, and now we are going to sneak this in here, and we're going to make a substitution right there. Okay, so let's see where we go from here. We now have VW is equal to 1/3 pi instead of RW we have 2HW over 5, and all of that is squared times HW. Okay, simplify that. VW is equal to 1/3 pi 4HW squared over 25HW. And continue simplifying it. We get VW is equal to 4 pi over 75 HW cubed. Now, it now becomes an awful lot easier to differentiate this. And excuse my coughing. It now becomes a lot easier to differentiate this. So differentiate both sides again with respect to time. And we get d VW dt is equal to, differentiate here, multiply down by the power. So 3 times 4 is 12 pi over 75 HW squared by d HW dt. Okay, and at this point we know dV dW dt, we know HW squared because we're asked to find this when the liquid is 6 centimeters deep, and the only variable that we have left that we don't know is dHW dt, which is what we're after. So if we fill that in, that's going to be minus 7 is equal to 12 pi over 75. We can leave that like that. You can break it down if you want, obviously, but you can leave it like that. H was 6. We were asked to do this when H was 6, so 6 squared dHW dt. And if we rearrange this a little bit, we get negative 7 times 75 over 12 pi times 36 is equal to dHW dt. And then that's something just to do on your calculator. And if you do that on your calculator, you get dHW dt is equal to negative 0.387 centimeters per second. Okay, now that was a long problem, and there were a couple of new things in there. So that's one that you take your time reviewing, and hopefully after a little bit of practice and do it yourself and keep going back and seeing what step am I missing, and if you do it a number of times like that, one line at a time, you will get there. Okay, thank you for watching. I know this has been a long one.